Okay, so you substitute in for psi minus, which is the bra. So it's the conjugate of the ket. So when you do the conjugate, you have to reverse the order in which the operators appear. So if you're substituting in using this equation, then the bra version of this is the bra of this, which that's fine. I did that. But then when you take the bra of this, you have to reverse everything. So the first thing comes is bra k prime. That's this. But then you have to put the v, because the v is right next to the ket. So then you have the v. Of course, it's daggered, but v dagger is equal to v. And then you put this operator. And this operator, daggered, is the same operator, except instead of a minus sign, you have a plus sign because it's the complex conjugate. And then after that, everything follows much more nicely than I had it before. So I got rid of all that nonsense I was writing. And then, so now it's fixed.
So I'm still not, I'm kind of confused. In the second line there.
Yeah.
From first line to the second line.
Now, well, that the rest of it was fine. So now I'm replacing this with the Lippmann-Schwinger equation, which is k prime, and then this stuff times the same thing again. That part of the derivation was fine.
Okay, so the ket version starts with v on the right, and later when you do that dot product, it goes to the left because of complex conjugate. Okay.
So
yeah, I was talking about 90, equation 19.
Equation 90?
Yeah, so v starts on the right. V is
yeah,
on the
but when you take the bra version of this,
right.
Then the v has to go to the other side because it has to stay next to the ket or the bra. So the v is over here because you're taking the conjugate, so the v has to stay with the bra, right?
Right.
I'm replacing this with bra ket k prime, bra k prime v, this stuff, which is just the conjugate of this equation.
And then from the third line to the last line, the whole thing is just the T matrix, k prime v psi k prime plus k prime v psi k prime, right?
For which line?
The last equation 91.
Equation 91, I just pulled out these factors, which are numbers now. And the thing left over is k prime v psi k plus, but I already derived back some
right
up here somewhere that's just equal to the T matrix. Yeah, the rest of the derivation was fine. I messed this part up where I didn't put the v in the right place, and then I decided that I could cheat and put it in the right place anyway by doing the funny complex conjugate thing. But it was just, it was a cheat. It wasn't allowed. But see, it's much simpler this way because now once you do it correctly, this h is already right next to the psi. So this h can act on the psi plus, and you just get ek. So okay, so no more cheating, and we're good. Any more questions about that one? This is related to one of your homework problems. So I don't know if any of you caught this. In the homework, it's relevant also. Anyway. So what else? More bookkeeping. I also kind of, it's not a cheat, but we were talking about having two identical particles. and I talked about their wave function as being a product of a spatial part, which is sort of assumed really all the relevant parts depended on the relative coordinate. So like, and then I also had some spin portion. We argued that for identical particles, this whole thing has to be symmetric or anti-symmetric. So either the spin part, if this can be symmetric or anti-symmetric, and then you have to combine that with the spatial part. It has to be, either symmetric or anti-symmetric, and then you do different combinations, like they're both either even or odd under particle exchange, and then depending on what you want, whether it's fermion or a boson, either if it's a boson, then they either are both symmetric or both anti-symmetric. If it's a fermion, then one is symmetric and the other one is anti-symmetric. But this only works if the spin and spatial degrees of freedom are independent of each other. And moreover, I was talking about combining the spin with the orbital angular momentum. So I was saying, well, we could, expand the relative, the spatial wave function in terms of spherical harmonics and do all that. But you can't, there's a big assumption about that. You can only do that if orbital angular momentum, L, is a good quantum number, meaning that, that we can diagonalize our Hamiltonian, using the YLMs, basically. So that's normally the case, but sometimes it's not. Sometimes orbital angular momentum is not a good quantum number, and you can't assume your states, are eigenstates of L. And well, actually, it's not that uncommon. It happens whenever you have, for instance, spin-orbit coupling. Sometimes in your Hamiltonian, there's a term that includes coupling between the orbital angular momentum and the spin. And that's actually quite important for chemistry, because electrons in atoms will typically have a interaction between their orbital angular momentum and their spin. So the kind of stuff we were talking about, it doesn't always work. You can't always just say, well, your wave function is just the product of the spin part times the product of just something that, has a well-defined orbital angular momentum for the spatial part. So that's also kind of wrong. And in fact, the thing that's these kinds of techniques are most often used for, like in chemistry, actually, in fact, you can't do that. And the spin orbit coupling does play a big role. And then, you have different eigenstates. You have eigenstates that mix together the spatial and the spin parts. And so then you can't really say what you get. It just becomes more complicated. Yeah, but the statement is still that if you have multiple electrons, then their total wave function has to be anti-symmetric under particle exchange. That's still true, but it's just not necessarily true that you can always combine the spatial and spin parts is just a product and just say, well, if one is even and the other one is odd. You can't always do that. Sometimes it's just more complicated. In fact, chemists have like a whole set of heuristic rules that take into account this kind of coupling, and those are called Hund's rules. So that's kind of interesting. So if you have this kind of coupling, then the way in which the orbitals fill up, we talked about Pauli exclusion, right? And how the fermions, if you're filling up orbitals in an atom, at most 2 electrons per orbital due to the spin, but it'll get more complicated with the spin orbit coupling. They won't fill up in a sort of way you would expect necessarily, because the spin orbit coupling can actually shift the energy levels around of the various orbitals, and so the ones that are lower energy are sometimes not the ones you would expect. And that's what the Hund's rules tell you about, is how do the electrons actually fill up the orbitals as you add more electrons to your atoms and fill up the periodic table. We're gonna move on and talk about second quantization, which is it's just a way of dealing with many particles, many identical particles. And again, the idea is that your states now are given by occupation numbers, where you tell me how many particles you have in each state. So these guys, the labels, the 1, 2, 3, these are the single particle states. Whatever they are, could be energy levels, what have you. And then the n sub I are your numbers of particles in each of those states. So for fermions, for instance, because of Pauli exclusion, n sub I is going to be either 0 or 1. Those are the only possibilities. For bosons, they can occupy the same quantum mechanical state, so you can have arbitrary number in there. But for the most part, for most of these states, you're going to have zeros everywhere, because you have to list all of the possible single particle states. So this is like an infinitely sized ket, right? You have to keep writing down all this. So like if you're have particles in a harmonic potential or something, right? Then you'd have to specify how many particles are in each energy level of the harmonic oscillator. And there's an infinite number of those. So you'd have to tell me how many are in the ground state. You could call that how many are in the first excited state. So this is, typically infinite. So the way we deal with it is we don't want to just keep writing out the whole big ket. We want to be able to sort of create these states by applying operators to some kind of reference state. And the reference state is going to be just the one where there are no particles. So we can define a state, it's called the vacuum, which is just the state where you got no particles anywhere. And then what you can do is you can introduce creation and annihilation operators, which pop particles in or out of your in and out of your state for at a particular energy level or at a particular quantum state. So what you want is you can define, for instance, a creation operator. And what it does is it'll say, I'm going to create a particle in state I. And so what that means is, what better happen is that if we take AI and we act with it on the vacuum, what we better get is a single particle in state I. And we can call that maybe K sub I or something. Oh, oops. K sub I. And this is the single particle state. This is one particle in state I. So that's kind of a sort of definition of it. And then for an annihilation operator, it's sort of the same thing, except we remove particle in, state I. So what would that look like? Well, that would mean that if you take the annihilation operator and act with it on a single particle state, where you have a single particle in state I, well, then you better get back out the vacuum. Or, if you're annihilating it in state J, then you better get 0 unless you're acting on the actual occupied state, and then you get the vacuum again. So that's a kind of property that the creation and annihilation operators have to satisfy. And, so, and this is sort of this definition, it doesn't really depend on the basis that you're using. So remember, so what is our space here? Our space is our Hilbert space is a tensor product of, a bunch of single particle Hilbert spaces, all of which are identical because they're identical particles. And we know that we can choose different set of bases for the single particle part. So we could choose the energy basis, we could choose, I don't know, some other basis, sort of doesn't matter, whatever we choose. And for each of those bases, we would have a set of, creation and annihilation operators, right? You can imagine these K sub i's being, a basis for the single particle Hilbert space. And we can convert between the different bases because we know how it works for a single particle. We know that in principle, the single particle states, we could write them as linear combinations of some other basis states, say call them L's. And all we'd have to do is just multiply by the coefficients associated with the change of basis. This is sort of from first semester, just changing basis for the single particle states. But it means that it's the same kind of rules, you can use this now to change your sets of creation and annihilation operators. For instance, we know that AI dagger acting on the vacuum creates one of these single particle states, which we can write as, sum over Q. And now this guy is going to be some other creation operator, right? B, which creates a particle in state Q acting on the vacuum. That's what LQ is, just single particle state. So that's like popping in a particle in state Q into the vacuum. And then these are just some numbers, the expansion coefficients. So if you look at this, we see that if you wanted to change basis, you would just have to take AI and replace it with a linear combination of these BQs. So there's a relationship there that AI dagger is equal to sum over Q BQ dagger, and these are just the expansion coefficients for a change of basis. So this is why this is nice, this method of second quantization, is because the little creation annihilation operators, they just behave in a similar fashion to what you would expect from like a single particle Hilbert space. But what they do is they actually pop in a particle into your system at that particular state that it's associated with. And of course, you can take the complex conjugate of this, and now you know that you have to dagger things. So hopefully my bookkeeping helped with this. So if you take the complex conjugate, you get daggers of these guys, and then you flip the order in which that inner product appears. So that's basically it. And then, of course, all of the kinds of particle statistics stuff that we've been talking about has to apply to these occupation number states as well. So what does that mean? If we go over here. So we can talk about the sort of particle statistics again. So imagine we have some state psi, which is one of these occupation number states. And imagine we take this state and we create a particle in it in state J, and then we create a particle in it in state I. Well, just like we argued for the multiparticle wave functions, the order in which you put in the particles can't change the state or make it physically different. So if you put the particles in the other way, where you first put in a particle in state I and then another one in state J, this can't change the state. They have to be equal up to a phase. Remember that phases are not observable. So in principle, you could have some phase that gets picked up when you put the particles in the opposite order. But this gives us pretty strong constraints on the operators themselves. It actually forces them to have certain commutation relations. And you can see that by recognizing that if we sort of subtract these two things, then we have a I dagger, a J dagger, minus E alpha ij. So this whole thing has to equal 0. And moreover, we know that we're allowed to change bases. So we can also change bases and change these A's to any other creation operators B. And that'll look like K, Ki, L, sub little l, K, J. And then you would have BK dagger, BL dagger, E I alpha ij, BL dagger, K dagger, and of course that also has to equal 0. So the fact that we can change basis and the fact that the order in which we put in the particles can't give us sort of physically any kind of physical difference, it means that the commutators between these creation operator is actually quite constrained. The only way that this equation can hold for any arbitrary state, psi, is if the individual terms in here vanish. And what that means is, since this is sort of an arbitrary transformation, this term has to vanish for all k and l. And moreover, so I can't really, this alpha ij can't really depend on I and j, because then you could always cook up some transformation that makes this non-zero. So it's really completely constrained. You have to have that, that the only possibilities here are that, of course, so it has to be that bk dagger bl dagger is equal to e to the I alpha ij bl dagger bk dagger. And more, so this can't depend on I and j, so this has to be some number. And if this is true, then of course this is true for any L and K, so I can just do this transformation again. And so this has to be equal to e to the 2I alpha bk dagger bl dagger. And now you see the only possibility here is that this thing is now equal to 1. This is really, if this is the same as what we did before for the multi-particle states, except it's just in this occupation number representation. And instead of having a constraint on the wave function, this gives you a constraint on the commutation relations of the creation annihilation operators. So if this is true, then the only possibility here is that e to the I alpha is plus or minus 1. And those are, again, the fermions and bosons, except now, it's in this other formalism. So what does it mean? It means that we have two different kinds of cases, right? The first case is where e to the I alpha is plus 1. And of course, I can make the same argument for removing a particle in state I and j. The same argument holds. So you'll have two cases. One is where e to the I alpha is plus 1, which means that these guys just commute, right? This is right. So if this is just 1, then this guy has to be minus this guy has to be equal to 0. So that means the operator just commute. So in the case that they commute, which again, the same argument holds for the annihilation operators. I can put all of them, I guess. So in this case, these are the bosons. This is the e to the I alpha equals 1 case. And the other possibility is that instead of a minus sign here, the operators come in with a plus sign and anti-commute. And these are the fermions. So those are the two cases. Either your identical particles are fermions or bosons, and their creation annihilation operators either commute or anti-commute. And anti-commutation is often written with the little curly braces. She'll do that. But look at this. I mean, if you have things that are anti-commuting, this automatically gives you the Pauli principle, right? Because if I is equal to j, then you automatically get that, AI is equal to 0. So you can neither remove two fermions nor add two fermions in the same state. You just get 0. And that's really nice, kind of very easy way of very easy way of seeing the Pauli exclusion principle right away from these anti-commutation relations. Any questions about that? So, okay. So now you might wonder, what about the mixed products? What about things like AI AJ dagger? Well, if I is not equal to j, then the same argument holds. You better have that AI AJ makes an indistinguishable state from AJ dagger AI. Right, because if we're adding a particle in one state and removing a particle in another state, it shouldn't matter what order we do that in. Those should be indistinguishable. So the same argument follows, that the wave function can differ by at most a plus or minus sign, and you get the same commutation or anti-commutation relations. So for fermions, yeah, so it has to be the same thing for these mixed guys too. So either the mixed ones anti-commute, then they're fermions, or if they commute, then they're bosons. But you might worry about what exactly happens if I is equal to j. And in that case, it's a little bit more subtle, because we know that we would be removing and adding a particle in the same state. So we'd have to do that case kind of separately. So let's see here, make sure I get this right. Yeah, I always get this calculation a little bit wrong. So all right, so tricky. So let's think about I is equal to j. And then you're adding and removing a particle in the same state. And if we look at this, then yeah, so what you should have, if this thing, this either the I alpha, which is the phase, if this thing acts on the vacuum, maybe this is the easiest way to see it. So what should happen here? What should happen here is if you annihilate the particle in state I, then that should just give you a 0. But if you create the particle and then annihilate it in state I, that should just give you a 1. So that should just give you back the vacuum state again. So that this whole thing should be equal to this, and then so this whole thing should be equal to 0 again. So either the commutator or the anti-commutator for the mixed states, it has to give you the identity. That's the only way to make this consistent. So it's not going to be 0 because when you act on the vacuum, it has to give you back the vacuum again. So what we'll actually have is that the mixed cases are as follows, that AK AL dagger minus AL dagger AK is equal to delta LK identity for bosons. And for fermions, it's the opposite because this e to the I alpha is -1. So then it's the anti-commutator. So this comes in with a plus sign. So it's a little bit different for the mixed states. They're not just 0, just. So I think there should be a little bit more of a rigorous way to do that, but I'll do that next time, I think. But I think it should be pretty clear when considering just the vacuum that the mixed commutator is going to be a little bit different, right? Because if you create and annihilate the particle in the same state, then you should get back to where you started. So that should just give us an identity. Notice this is different if I and J are not equal to each other, then the same argument doesn't work, right? Because then I'll create a particle in some state J, but then I'll annihilate a particle in some other state I, but there's nothing there because it's the vacuum, and so that should just give us 0. So this is a little bit different when you're popping a particle in and out in the same state. It should give you the identity. But it'll depend on the precise relationship. It'll depend on sort of the this e to the I alpha factor. So this isn't quite the full thing, but I'm comfortable writing this because I think it's clear. I've yet to find a good proof of these commutation relations. It's sort of I feel good about. So I'll look. I'll try to do it next time. But I'm sorry, I'm unhappy what I did last year, so I'm not gonna. I'll think about it. But these are the important relationships here, that either your creation annihilation operators commute or anti-commute, and in the special case when you have these mixed operators, then they either commute or anti-commute unless they're in the same state, and then you pick up an identity. But you see, it's the same sort of deal as the harmonic oscillator raising and lowering operators. They behave in the same way. The bosonic ones, anyway. Fermionic ones are a little bit different, I guess. But this guy, if you remember, the commutation relation for the raising and lowering operators for the harmonic oscillator was equal to the identity. So this is quite similar. It's just saying that if you have raising and lowering operators between different states, then they just commute. They all commute for bosons. But if it's in the same state, then they behave like the raising and lowering operators for a harmonic oscillator. And it makes perfect sense, because what you're doing for the bosons, you have some state I, and you're either adding a particle or you're taking a particle and removing it. And that's like moving up, and that's like adding a quantum of energy to it's like moving up and down the ladder of the harmonic oscillator. Same mathematics. Okay. And of course, you can, just as in the harmonic oscillator case, you can construct number operators. And sub I. And just as in the harmonic oscillator, it's just going to be AI dagger AI. And what does this do? Well, if you act with it on one of your occupation number states, you know, it'll, for a particular state AI, what it'll do, it'll just pick out that number. It's an, this is the occupation number state is an eigenstate of this operator, and the eigenvalue is just the number of particles in that state. And yeah, so, and remember for fermions, the occupation number is going to be either 0 or 1. Okay, so you have the number operator. You can also get the normalizations of these operators in a similar way as the harmonic oscillator. They're sort of exactly the same. So if you have AI acting on one of these occupation number states, which I'll call sort of big psi, then the normalization is square root of ni for the annihilation operator, right? And then for the creation operator, it's square root of ni plus 1. It's just by the same argument as the harmonic oscillator, raising and lowering operators. So you can use these operators now to construct any given occupation number state from the vacuum. And what's nice about it, the reason we do things this way is because all of the particle statistics, you know, what happens under particle exchange, it's captured by these commutation relations here. And so whenever dealing with these multi-particle states, what you do is you always just have the vacuum, and then you have a bunch of creation and annihilation operators acting on the vacuum. And then if you want to figure out what happens, you just do a bunch of, you just commute the operators around. And that's kind of, that's sort of the kinds of things you do with these multi-particle states in the second quantization formalism. So what do I mean? You know, any occupation number state now I can write as a sum over all of the different occupation numbers. And so any state, of course, I can write as a linear combination of occupation number states. And so I'm gonna sort of write it like this. So what I mean by this is any state in my multi-particle Hilbert space I can write as some linear combination of occupation number states, where this is just a set of occupation numbers. It's just one of these guys. So now maybe I'll call this phi, something more general. It's a linear combination of any one of these psi's. You sum over all the possible, or you sum over all the occupation numbers, sets of occupation numbers that you want in your linear combination. It's the general state. So any phi that's in our big Hilbert space, which remember is a tensor product, infinite tensor product of Hilbert spaces, or actually, just whatever n is, the number of particles. Any one of those states you can write as a linear combination of the occupation number states, which is sort of the basis that we're using. And each of those states we can write in terms of the vacuum, because we know how to use the creation annihilation operators. So you have your coefficients n sub I, and you have your normalizations. And what do we have to do? We have to apply the creation operator, right? N sub I times for each of those single particle states I. So what you'd get is, for sort of state 1, you'd apply it n1 times. For state 2, you'd apply it n2 times. And each time you pick up a factor of square root of n sub I each time you operate, and that gives you this factorial for the normalization, and so on. And if you remember, this is exactly how you can construct the wave functions for the harmonic oscillators. Some similar thing happened there with this normalization. Just comes from the normalization of the creation annihilation operators. And what you're doing is you're creating particles, however many you need, in the different single particle states. So you create a particle in state 1 and 1 times, a particle in state 2 and 2 times, and so on. And you pop all those in to the vacuum. So what it means is that any state of interest that we might have for our multi-particle system can be written in this fashion as a linear combination of different occupation number states, and all the different occupation number states I can write as the vacuum being acted on by all these creation operators that pop in the right numbers of particles in each of the single particle states. Yeah, so that's basically the way second quantization works. And what we have to do now is also figure out how operators work, right? We have to figure out how we actually act on these states. So that's kind of the next thing to do. But let's talk a little bit about Pauli exclusion again to see it in another way. Any questions, though, about this formalism and what we're doing? So again, the idea is that our Hilbert space, right, which includes, you know, n tensor product of n different single particle spaces, can be represented using occupation number states. That's sort of like our basis for that space. And so any state is going to be some linear combination of the occupation number states. And each of those states we can write as follows in terms of the creation operators. And that makes it very nice because now all of our mathematics reduces to operations with the creation annihilation operators, right? Because the only thing left over here, other than these coefficients, are these operators and then the vacuum. So the vacuum's always there, but we've reduced everything to just these creation operators, which have well-defined commutation relations or anti-commutation relations. So we can sort of flip them around, things like that. But here we go. Another demonstration of the Pauli exclusion principle is simply that if you try to create a particle in the same state twice in the vacuum, that's of course equal to minus that, because these operators anti-commute. And so you conclude that you just get 0. It's not possible. The other issue with the Pauli exclusion principle and fermions, well, fermions in particular, is that because of this funny anti-commutation property, you have to be careful the order in which you list your single particle states, because we know that, so this is when I is equal to j. If I is not equal to j, you, of course, it's the same thing. You know that ai dagger, aj dagger is equal to minus aj dagger, ai dagger. So when you first list your single particle states, like here, 1, 2, 3, you have to pick some convention for listing them, because, you know, if we flip that convention, then your wave function will pick up a minus sign. So that's a kind of subtle issue that you need to know for fermionic multiparticle states, is that you have to have a well-defined sequence of the single particle states, because if you flip that sequence, the anti-commutation property will give you a minus sign. So you have to, so in particular, okay, so say you create 2 particles, right, in state I and j into the vacuum, you know that'll be a particle in state I and a particle in state j, right? That's some 2 particle state. You see that has to be minus the 2 particle state where the other, you know, the first particle is in state j and the first one in state I, because this is equal to minus aj dagger, ai dagger. So you have to be careful. You have to have a specified order in which you list the single particle states. So something to keep in mind. What else? And of course, you know that you can change basis for these creation annihilation operators and move between different sets of single particle states. And again, those things are done by just unitary transformations, where these guys, these matrix elements, are just the inner products between the single particle states. That's sort of what we had before. And similarly for the creation operators, so that's kind of it. So now we're going to talk about operators. And yeah, any questions though about the setup? I'm going to erase all this because we're running out of room. Okay. Any questions, comments, concerns? Trying to go slow is sort of hard to. Stuff's pretty unintuitive, at least to me. Okay, so what about operators? Okay, so one of the easiest operators is the sort of the total number of particles. That's an observable. And what it is, of course, it's you call it squiggly n. You're going to sum over all the single particle states, and you're just going to add up the numbers in each of those single particle states. And that has to be sum over I, AI dagger, AI. So, so that's like the first easy operator to do. And what you notice right away is that your operators, right, they're going to be some linear combinations of the creation and annihilation operators, because those, we know how those act on the occupation number states. And if we write everything in terms of our occupation number basis, then, you can write any operator you want as some combination of the creation and annihilation operators. So really, again, just the operator part also reduces to just messing around with these raising and lowering operators. So, okay, what about something like the energy? The energy can be more complicated because you might have interactions between the particles. But if you're just worried about, say, adding up the energies of all the single particle energy levels, well, then you could just say that your single particle operator, well, this thing is just going to be a sum over your single particle states. Then it might be the energy associated with a single particle in state I, and then you would just multiply by the number of particles that are in that state. Like that. But in general, though, your basis doesn't have to correspond to, it doesn't have to be diagonal. So in general, any kind of operator like this single particle operator, it could, in principle, be a linear combination of including off-diagonal elements. So in principle, you could have something like this. This would be a single particle operator, because it's not, these AIs don't necessarily have to correspond to the states that diagonalize the single particle Hamiltonian, for instance, because we know we can choose whatever basis we want. And in that case, in general, you would have an operator like this. And if we think about what this does, how do we know that this is a kind of single particle operator? Well, we can think about what happens to a single particle state. So what's a single particle state? Particle state. What is a single particle state? Well, you take the vacuum and you put a particle in it at some state I, and that's a single particle state. And in terms of the occupation number, of course, that's going to look like zeros everywhere except for the single one in the place where you put the particle in state I. So now let's take this thing and act with this operator on it. We'll take H, which I claim is a single particle operator, and we'll act with it on this state I, the single particle state. So what does that look like? Well, I can get a sum over, I have to change my index here so that I don't accidentally put two of the same index. And you got KL1, and you have AK dagger, AL, and then you have the AI dagger acting on the vacuum. Now, if we look at this, we know that what will happen. So if we look at this, the only place where this AL, right, will actually give us something non-zero is when it acts on state I, right? Because we pop in a particle in state I and then we remove a particle in state L. So this is going to vanish unless L is equal to I. And we know that that's the identity. So this thing is equal to K, H, K, I, 1, A, K, dagger, acting on the vacuum. And what is this thing? Well, this thing is creating a particle in state K. Right? So this is a single particle state, state K. So what we found is that this operator behaves just as like you would expect a single particle operator would behave, right? What it does is, in general, if you act with an operator on some state I in our Hilbert space, you'll get a linear combination of your basis states for that single state, and that's exactly what happens here. You get this. So this expression just looks exactly like you would have in a single Hilbert space, like just one of them, the single particle space. And that means that what are these matrix elements, these HKIs? Well, they must be just the matrix elements in that single Hilbert space, single particle Hilbert space. Like that. That's what they are. So that's a single particle operator. You can see that by its construction, it behaves just as we would expect. And now you can do another interesting thing and see how these operators, single particle operators, act on two particle states. You can see what happens there. And then it becomes a little bit more subtle. But any questions so far? So again, this is a general form of a single particle operator. And what I mean a single particle operator is that it should, on a single particle state, it should behave just like you would if you had a single particle Hilbert space, right? It just transforms the state in exactly like an arbitrary operator would, just via vector matrix multiplication. That's exactly what we found. But now, of course, once you have this operator, you can ask, well, what will happen if I say act with it on a two particle state? So let's look at that. If we have a two particle state, well, I can call that I comma j. And again, you have to forgive me, but it's sort of, we're going to have to sort of go back and forth between the occupation number representation and then things we know, like single particle kets. This is a sort of two particle ket. It's just convenient because what we're trying to do is connect stuff we know, like single particle states and two particle states, to this occupation number formalism, which isn't always so intuitive. So you can kind of hop back and forth. But if you ever have a question which ket represents what thing, you should just ask me, because it can get a little confusing. So okay, the two particle guy is going to be a I dagger, a j dagger, right, acting on state 0. I guess I'm out of time, but we'll continue with this. We'll see what happens when you take this single particle operator and act with it on a two particle state. And naively, what do you think should happen? Well, what should happen, right, is that it should act on those two particles sort of independently, because it's a single particle operator. And we'll see that it does, but there will be a difference between fermions and bosons in that there will be a relative phase difference between the two. So we'll see that. But again, what I want you to get out of this class so far is that we've converted all of the particle statistics and symmetrization, anti-symmetrization, to properties of these raising and lowering operators. That's what second quantization gives you, is it does all the bookkeeping for you, keeps track of everything through the commutation relations.